Hello class, Adam Ward here. I wanted to work through an example similar to example 4.2 in your textbook. In this example we've got a series of chemical compounds that are related to each other through two rate constants. Given information about the rate constants, the critical concentration in B, or the maximum concentration of B that we ever see, and knowing that we don't have any B initially, meaning all of our chemical is in compound A initially, what is that initial concentration for A, or what happened in A at the starting point? Now, this is a case of chemical reactions occurring in series. We discussed that as a very close parallel to Lake-Syn series in some of our previous courses. So we've got an exponential loading from A to B. If we start with a load in A is going to convert all of that mass into B. It's going to do so at a rate that has an exponential decay. And so beta E describes that loading to species B, and typically lambda would be used to describe our removal. That's for lakes. And when we're talking about chemical species, what that means is rate constants. Beta E is K1, that describes how B gets created. Lambda is K2, that describes how B is removed. And so with that in mind, given some information about critical concentrations, let's start with critical concentration equation shown here. We know the beta E's, we know the lambdas. What we don't know so much about is loading and volume. And we also don't have that initial concentration in A anywhere in the equation. And so my approach is then to look at the things I don't know and figure out how they're related to what I want, in this case initial concentration of A. We could write out our general solution for species A. This is similar in form to equation 3.23 in your textbook, the difference being we don't have any settling or outflow terms, so I've zeroed those out already for you. And now we've got a W over V that we're thinking about. We see it's related to the concentration in A, and we see it's related to the rate of accumulation, dc dt. And so we can realize that at time 0, there is no time rate of change of species A. It only starts to change when we let time start to move forward. And so at time 0, we end up with the loading divided by the volume equal to the initial concentration in A times reaction rate K1. We can make that substitution back into our critical concentration equation. Now looks like this. And we've got one equation, one unknown, the concentration of A at time 0. We can substitute in all concentrations in milligrams per liter and all rates in per day. And if you go through the algebra, you find a solution of the initial concentration in A at 46.9 milligrams per liter. And so what we're seeing here is that our equations for lakes are actually complicated versions of the equations that we well know from our chemistry courses. I hope this example helps you.